Hello students, welcome back. Let's go to section 3, so-called linear substitutions, even though it's not really linear. Names can be deceiving, but for historical reason it is called linear substitution, but in fact it is not linear. Let's suppose an equation, let's suppose a differential equation of this kind of form. The derivative is function of at plus by plus c form. And we take this entire part inside at plus by plus c as some other character, say z, and then go from there. And this one is first degree polynomial, so people began calling it linear. But in terms of linear algebra, in terms of precise definition of the linearity, it's not linear. Without this plus c, if we have just at plus by, yes, then it's linear. But plus c, because of that, it's not linear in strict form. It should be called affine substitution. That would have been correct terminology, but then again, it's too late to change anything. This kind of thing we're going to call linear substitution. So once you have something like this, what do? Well, again, this is differential equation, so you have to take the derivatives. Let's take the derivative of z, and this is what we get. Take the derivative. Z prime is a plus by prime, and what is y prime? What is y prime? This whole thing is y prime. This is y prime. That's y prime, and that's f of z. So what did we end up with? We ended up with an equation of z only. A is constant, b is constant, z prime is equal to some expression of z only. So this is again a separable equation. Let's go to an example problem, and here's a nice example. We have t plus y plus 1. So this whole thing is at plus by plus c form. Here's another example, at plus by plus c form. In this case, c is 0. In both cases, we can use that linear substitution, or a little bit more precisely speaking, affine substitution. Okay, here we go. Z is equal to t plus y plus 1. Then what is z prime? That's t is 1. Derivative of t is 1. And then derivative of y is y prime. Okay? But then again, what is y prime? This whole thing. Oops, I need 1 plus. But then again, did you say this entire thing inside is z? So this is z squared. Are you with me here? So what did you get? We got a separable equation. Is equal to 1 plus z squared. And we can use the separation of variables. 1 over 1 plus z squared dz is equal to 1 times dt. And we can take the antiderivative of both sides. Let's continue here. That's equal to antiderivative of just 1. And then what is this? Antiderivative of 1 over 1 plus c squared. That's arctangent. That's equal to t plus c. And let's see. We're almost there, but z is t plus y plus 1. So let's rewrite everything in there. Arctangent of t plus y plus 1 is equal to t plus c. And I guess that's it. We have an implicit solution here. And I don't think it is possible to solve it with respect to y explicitly. Shall we check? Okay, let's check. Arctangent of t plus y of t plus 1 equals to t plus some constant c. That's the equation. No, excuse me. Yes, that's right. That's the equation here. Yeah. And take the derivative with respect to t implicitly. That's what you get. Now, here, I want y prime equals to something. So solve this thing with respect to y prime. Solve the previous result with respect to y prime of t, and let Mathematica handle it. What did... Oh, excuse me. I made a typo here. Sorry about that. Arctangent of... No, I didn't make any typo here. Why am I having... Oh, this is correct. It just, they just break up the complete square. Yeah. They just broke up this complete square. That's about it. So, okay, how do I make sure this is what we have here? Simplify this expression here that Mathematica just sped out minus this one, t plus y of t plus 1 total quantity squared, and subtract one from the other and check, equal to 0. So they're the same. So just by looking at this, it looked like I didn't get what I wanted, but that's because that expression and this expression were the same as we checked over here. Sometimes that happens when you deal with computer algebra system. You gotta know mathematics, real mathematics, in order to use it. How about the next problem? Well, this is going to be my new character z, so negative 2t plus y. And now let's take the derivative, minus 2 plus y prime. But then again, what's y prime? Y prime is this. So we have negative 2 plus, that's y prime, but that's z, isn't it? Always that's z. So this whole thing is z squared. So simplify just a little further, z squared minus 9. That's where we get. All right, let's go ahead with the separation of the variable. 1 over z squared minus 9 dz is equal to dt. You see, z prime here is, no, I'm skipping a step. Let's keep it at that and then go ahead with one more step. Squared minus 9 and dz is equal to dt. And then let's take the antiderivative of both sides. Let's see, what's the antiderivative of the left-hand side? Right-hand side is going to be easy. Left-hand side is going to be a bit of a problem. Right-hand side, I'm going to get t plus c. But here, how do we handle this? Z plus 3, z minus 3. factor this, and then take the decomposition by partial fraction. 1 over z minus 3 minus 1 over z plus 3. Oops. And I must be missing something here. Let's see. Z plus 3 minus of another z minus 3. 3 plus 3, so the total will be 6 here. I have to undo that 6. There you go. That's going to be correct decomposition by partial fraction. And then let's see. That equals to 6t plus 6c, and that can become as a new character. I'll do that later. And then that's going to be log of x minus 3 minus, no, z minus 3. Z minus 3 minus log of z plus 3 equal to 6t plus 6c. And what's the typical technique to work out these two logarithms? Combine them into single logarithm, log of z minus 3 over z plus 3. And then to the right hand side, 6t plus 6c. Well, we have an implicit solution here, but we can do better, and we should be able to do better. And way back in lesson 2a, I think we discussed how to take care of this kind of situation in a great detail, including how to deal with inside of the logarithm so that inside is always positive, yet no more problem. Remember, take the exponential of both sides. So we have the inside, z minus 3 over z plus 3. And then the right hand side is exponential of 6t plus 6c, and I'd like to have bigger font here. And then I hope everybody remembers, how do we take care of this? Times exponential of 6c, and then this is constant, right? Take this as a new constant, say k. Now we can allow k to be negative. If this inside had been negative or something, then this whole thing does not make any sense, so we may need absolute value with c1 and c2, c3 and c4. Looks like you may need many possible integral constants and so on. It can get really messy. But by doing this, by taking this constant out and allowing this constant to be negative as well, you can take care of all those. In short, z minus 3 over z plus 3 is equal to k times exponential of 6t. Right here, we don't have to worry about the domain issues. Of course, the denominator should not be 0, but otherwise okay. All right, we have a little bit better implicit solution, but can you actually get explicit solution here? Yes, we can. Yes, we can. This is linear fractional equation, so we can solve it. Flip denominator to the other side. Z minus 3 is equal to k times e to the 6t, and then flip the denominator over to the other side, c plus 3, and then break up the parentheses. C minus 3 equals 2 k z exponential of 6t plus 3k exponential of 6t. Did I do this right? Did I break up correctly? Now I have z here and then another z term there, so get both of them together. Z minus kz e to the 6t in one side, and then this 3 flip it over to the other side, so positive 3 plus 3k exponential of 6t. Is that an improvement? It may not be completely apparent yet, but yes it is, because I can factor z out. Z 1 minus k e to the 6t is equal to 3 plus 3k exponential of 6t. Almost there. I'm going to flip this to the other side and I'm going to get z equals to 3 plus 3k exponential of 6t divided by 1 minus k exponential of 6t. Let's expand the font. I guess that's it. As far as z is concerned, we have it here. But then again, what was z? So let's go back. Negative 2t plus y is equal to this thing. Let me expand the font. So y is equal to this linear fraction plus 2t. And I guess this is the final form. Well, shall we check? 3 plus 3k times e to the 6t 1 minus k times e to the 6t plus 2t, and then what is the differential equation here? Simplify y prime of t minus the right hand side, this thing. Minus minus plus, and this is not y, it should be y of t. And let's see, is it really 0? Yes, it is. Everything is correct. Here is the full solution. Well, let's remove this, and I can get not just the full solution, but also the verification as well in the same viewing window. Okay, there you go.